In the far future, the universe does not end with a bang. It fades with patience. Stars grow dim. Heat spreads thin. Space looks empty. Not because nothing exists, but because contrast slowly disappears. Tonight's journey follows the last lights, the cooling remnants, and the soft background glow that never fully goes away. If this kind of calm science storytelling is your thing, please like the video and subscribe for more long-form sleep documentaries. It helps the channel grow, and it tells the algorithm to bring you the next quiet voyage. Now, settle in. The darkness ahead is not a threat. It is a slow cosmic silence. A universe filled evenly with matter would look calmer than the one that exists. The overwhelming emptiness is the mechanism that lets structure appear at all. In that region between galaxies, space holds less than 1 atom per cubic meter on average. That thinness is like a dune field where a single seed appears only after many ridges. The first unlock is simple and quiet. Nothingness is not a blank backdrop. Nothingness is the stage that sets the rules of distance and time. A slow scene opens on a dark gulf where almost no glow gathers. Only a faint smear of light marks a distant ridge. The darkness is not uniform, it has a gradient. It deepens toward the middle, it softens near the edges. The emptiness has shape, it has boundaries made of slightly richer gas and slightly more frequent galaxies. This is where the title begins to feel true. The universe is empty for a reason. The reason is not a single event. The reason is a long sorting process that starts small and ends vast. One concept carries the whole section. The cosmic web is the large-scale pattern of matter in space. It forms filaments and sheets around enormous voids. A second concept sits inside the first. A void is a region with far less matter than average. The emptiness is not absolute. It is a relative hollow. The third concept is gentle but decisive. Expansion increases distances over time. It stretches the gaps as the web takes shape. Another visual anchor arrives with a calm shift. A broad basin of darkness appears like a still pool between faint strands. The strands curve. They look like braided river channels seen from high above. After floodwater drains, silt remains in thin lines. Wide flats stay bare. The analogy is not perfect. The unlock is what matters. Gravity gathers what it can. Everything else is left behind as open volume. The filaments are not solid ropes. They are gradients. Density increases toward their centers. It falls away toward the void interior. Along a filament, clumps appear like beads. A bead is a galaxy group. A brighter bead is a cluster. The physical detail is quiet but concrete. The edge of a void is a wall. It is a sheet where matter is slightly compressed. Light passing near that sheet bends by a small amount. The bend is subtle. It still reveals a boundary. A payoff follows the image. Emptiness is not the absence of structure. Emptiness is the shape of structure seen from the inside. The scale shifts without strain. The same sorting can happen in a drop of mist. Droplets drift together where air currents converge. Clear pockets remain where currents diverge. Now the scale lifts to cosmic size. The convergence is gravity. The divergence is expansion. The same logic repeats across eons. The next unlock is about origin. The web does not start as lines and walls. It starts as tiny differences in density. The differences are so small that they can be missed in any single place. Over long time, gravity amplifies them. Where density is slightly higher, pull is slightly stronger. Where pull is slightly stronger, matter flows inward a little more. The flow is slow. It is also relentless. Voids form because matter leaves them. Filaments form because matter arrives there. A scene slows down on an edge. A faint arc of galaxies traces a curve. The curve is the rim of a void. The rim is not sharp like a cliff, it is more like a fog bank that thickens by degrees. Inside the fog, the view fades. Outside it, faint points become more common. The physical detail is a layering. Density layers from low to less low. The payoff is a quiet answer. The universe does not become empty by losing matter. It becomes empty by moving matter into narrower places. Expansion helps by stretching the distances between those narrow places. A second number arrives with care. A large cosmic void can span about 100 million light-years. That span is like an ocean basin compared with the thin foam lines at its rim. The comparison is not about travel, it is about proportion. The rim is thin, the interior is broad, the interior dominates volume. This is why emptiness matters. Volume is where most of space resides. A few bright nodes can look important. The web reminds a different truth. Most of existence is the space between knots. Another visual anchor appears as a slow drift through the interior. The darkness is not perfectly black. It holds a faint haze of gas. It holds stray photons crossing from far away. It holds occasional isolated galaxies. Those galaxies are like lone shrubs on a plain. They are not the rule, they are the exception. The payoff is a subtle shift in meaning. A void is not empty in the everyday sense. It is empty in the statistical sense. It contains far less than average. It also contains the cleanest record of expansion. In an underdense region, gravity has less material to grip. The web relaxes there. Expansion can pull more freely. The void gently grows more empty relative to the walls. The gradient steepens over time. The boundary becomes more defined. Another scale shift arrives. In a short span, nothing seems to move. In a long span, everything rearranges. The change is too slow for intuition. It is still real. This is where a limit of observation enters. A void cannot be weighed directly by looking at its interior glow. The gas is too thin, the light is too faint, the signal is diluted by distance, the boundary is inferred from what outlines it. Galaxies trace the walls, light bending traces the mass. Subtle temperature patterns in background radiation can carry hints. Each method is indirect, each method has resolution limits. A coarse measurement blurs a sharp boundary into a soft one. A sparse sampling can miss a thin filament entirely. A selection that favours brighter galaxies can exaggerate emptiness. The payoff is calm and grounded. Knowledge of cosmic emptiness is a mosaic. It is assembled from outlines and gentle distortions. Certainty has a texture. It is smooth in broad strokes. It is grainy in detail. The section returns to the web as a guiding picture. Filaments do not fill space. They thread through it. Sheets do not cover the whole sky. They form partial walls. Nodes do not dominate volume. They dominate brightness. The emptiness is terrifying only if emptiness is mistaken for nothing. The more accurate view is quieter. Emptiness is the majority condition. It sets the distances that light must cross. It sets the timescales that processes require. It sets the isolation that grows as expansion continues. Another visual anchor closes the loop. A faint filament arcs across a vast hollow. The hollow is so broad that the filament looks like a hairline crack in dark stone. The crack is bright only by contrast. The stone is not carved away. It is simply left unfilled. The final payoff arrives as a gentle promise. If voids dominate volume, then voids control perspective. They shape how patterns appear. They shape what can be inferred from light. The next section moves closer to the void itself. Its basin-like geometry becomes clearer. Its edges become measurable without any need for drama. A void does not feel like an absence so much as a quiet geometry. Its shape comes from matter sliding outward and gathering into a rim. At this distance, a large void resembles a shallow basin in 3 dimensions. The interior is dim and sparse. The edges appear as gentle walls made of slightly denser filaments. The first unlock is simple. A void is defined more by its boundary than by its centre. The boundary is where the web tightens. The interior is where the web loosens. A slow visual scene forms in the mind. A broad hollow opens in darkness. Around it, a faint ring of galaxies traces an incomplete circle. The ring is not uniform. It thickens in places. It thins in others. A boundary looks like a layered fog in cross-section. Density rises gradually toward the rim. It drops steadily toward the middle. The physical detail is a gradient that can be imagined like a slope. It is not a cliff. It is a long incline. The section keeps three concepts only. A void is an underdense region. It has less matter than its surroundings. The void profile is the way density changes from center to edge. Expansion is the steady stretching that increases separations over time. Everything else stays quiet and visual. In that region, motion is slow. Matter drifts as if along shallow channels. The drift is not a stream that can be watched. The drift is a statistical flow. It is the sum of countless small pools. A second visual anchor arrives as a calm checkpoint. The rim of the void shows a thin sheet of gas. The sheet is not bright. It is only slightly more present than the interior. Along the sheet, faint clumps appear like knots on a loose net. The net hangs in darkness. It holds shape by tension. The payoff is clear. A void is not carved out by removing matter. A void emerges because matter has more time to leave than to return. Gravity pulls toward denser places. The interior has less pull. The result is a gentle evacuation. A main number grounds the scale. The edge of a major void can be about 100 million light-years from one side to the other. That span is like the distance between two distant coastlines with an almost empty ocean between. The comparison stays calm. The point is breadth. The hollow is wide enough that a single rim can feel far away in every direction. Another scene settles on the void interior. A small handful of isolated galaxies sits in the darkness. They appear as rare points against a deep background. The spacing between them is large. The emptiness is not perfectly smooth. It has subtle texture. Slightly denser patches sit like faint smudges. Slightly emptier patches sit like clearer pools. The payoff is a quiet correction. Voids are not featureless. Voids have internal structure. The structure is weak. It still matters. It decides how the void grows. It decides where the rim thickens. It decides where thin tendrils survive. A scale shift arrives without strain. In a small room, dust motes drift in slow air. They do not spread evenly if air is still moving. They gather near subtle currents. They leave cleaner pockets behind. In cosmic space, the currents are gravity and expansion. The dust is matter. The pattern grows from tiny differences. Over long time, the differences become boundaries. The boundary is a physical story. Density changes across it. Pressure and gas changes across it. Temperature can shift slightly across it. The rim can show a soft layering. The interior can show a smoother field. Another visual anchor continues the journey. A sheet on the rim bends into a shallow arc. It looks like a curved membrane. It is not solid. It is a preference for where matter sits. The membrane meets a filament. The filament is like a narrow ridgeline. The ridgeline is brighter than the sheet. It is still faint. The payoff follows the image. Voids connect to each other. Rims meet. Sheets intersect. Filaments bridge between nodes. The universe is not a set of separate holes. It is one continuous foam of hollows and walls. The next checkpoint reaches the limit of intuition. A human mind expects emptiness to be stable. A human mind expects a cavity to stay the same size. In cosmic space, the cavity changes because the background changes. Expansion increases all separations. The void interior has less gravity to resist that stretch. The void can widen relative to denser regions. The rim can sharpen in contrast. The interior can become more underdense relative to the average. This is a slow amplification. It is not dramatic. It is persistent. The section now touches the limit of observation and names it clearly. The true shape of a void cannot be seen directly as a filled volume. The interior light is too sparse to trace every contour. Any picture made from galaxy positions is incomplete. It samples only where galaxies exist. Thin tendrils can be missed. Small clumps can be absent from the record. The boundary can look smoother than it is. Another limit follows. Distance estimates have uncertainty. A small error in distance can smear a sharp rim into a thicker wall. Motions along the line of sight can stretch features in a map. A round void can appear slightly squashed. A long void can appear more round. The payoff is calm and immediate. The most reliable facts are broad. Voids are vast. Voids are underdense. Voids are bounded by walls and filaments. The fine details remain softer. They are inferred through patterns that repeat across many regions. Another visual anchor arrives as a slow closing image. A cross-section through the void shows a shallow bowl. The center is the lowest point. The rim rises gently. The rim is uneven. It has thicker ridges and thinner passes. The bowl is not carved into rock. It is carved into probability. Matter is more likely to be on the rim. Matter is less likely to be in the center. The final payoff settles the section into the arc. The emptiness has an outline because gravity and expansion cooperate. Gravity gathers into lines and sheets. Expansion stretches the gaps between them. The next section moves from shape to cause. Expansion itself becomes the quiet engine that keeps the hollows wide and the walls far apart. A quiet change shapes every distance even when nothing seems to move. Cosmic expansion steadily increases separations and emptiness grows because space itself grows. At this distance, a sparse field of pale points seems suspended in blackness. No point slides across the field like drifting grit. The spacing between points slowly opens as if the background relaxes. The first unlock is simple. Expansion is not travel through space. Expansion is the scaling up of space itself. The scene holds still, yet the measure between points grows. Only 3 ideas guide this section. Expansion is the steady growth of distances between far separated regions. Scale factor is the relative size of space compared with earlier. Redshift is the stretching of light as space expands. One term receives a short definition and then returns to plain language. Scale factor is the relative size of space compared with earlier. A sponge that slowly swells in water offers a gentle analogy. Dark mineral grains sit inside the sponge and stay where they are. As the sponge expands, the grains become farther apart without drifting across the material. The reason it matters is immediate. The same pattern can look the same yet become larger everywhere. A visual anchor holds the idea in quiet geometry. Thin translucent threads link nearby points into loose triangles. The triangles keep their angles for a long time. Their sides lengthen by a small amount across long time. The geometry stays familiar while the scale drifts outward. Another small unlock follows. A void can widen without being swept clean. The void widens because the background scale increases, while local clumps remain locally coherent. A physical detail makes the abstraction tangible. Light from a distant galaxy arrives with its wavelength stretched. Dark absorption lines in its spectrum shift toward longer wavelengths in an ordered way. The pattern slides rather than smears. A kelp ribbon in a slow tide offers a quiet image. Small ripples along the ribbon become farther apart as the ribbon lengthens. The ripples remain ripples. Their spacing changes. Redshift is that spacing change for light. One main number anchors the timescale. Expansion proceeds for about 14 billion years like many cycles of ice ages on Earth. The comparison stays gentle. The point is patience. A change too small for a moment becomes a rule over eons. Another visual anchor arrives to keep the rhythm steady. A filament at the edge of a void appears as a dim ridge with a soft inner slope. The ridge is not a hard wall. Density rises gradually toward it. The interior falls away from it. Along the ridge, faint clumps appear like beads on a dark cord. The interior holds only rare points in a weak haze. A payoff follows the image. Expansion and gravity do not cancel everywhere. They negotiate by region. Dense regions hold together because gravity is stronger there. Underdense regions yield more easily because gravity is weaker there. In an underdense region, inward pull is weaker and less coordinated. The local stretch faces less resistance, so the void interior widens a little faster than its walls. The profile changes in a specific way. The center becomes more rarefied relative to the average. The rim becomes more contrasted relative to the center. A slow scene shows the ridge standing out by comparison as the basin broadens. The unlock is immediate. Expansion does not merely separate structures, expansion also deepens the contrast between ridges and basins. The section shifts scale without strain. In a thin fog over a cold plain, thicker patches form where air settles. Thinner patches persist where air rises and spreads. The contrast is slight at first. Over time, the contrast becomes clearer. In cosmic space, early density differences are tiny. Gravity amplifies them into ridges and basins. Expansion stretches the separations that result. The web appears as a compromise between gathering and spreading. Another payoff arrives in plain language. The universe becomes empty in volume because structure becomes narrow in shape. Lines and sheets take up little space. Basins take up almost everything else. A limit of intuition enters softly. Intuition expects expansion to have a center and an edge. Cosmic expansion has no preferred center in that sense. Any large region sees other large regions receding on average. Intuition also expects something to expand into an outside. The better picture is internal. Distances scale up within space and the pattern keeps its overall form. A fresh visual anchor steadies the thought. A faint circle of points keeps its roundness while its circumference grows. The circle does not drift toward any external boundary. The distances within the circle simply increase. A limit of observation follows and names what breaks down. Expansion is not measured by watching positions shift from one day to the next. The change is too slow on short spans. Distances are inferred from light and that inference is indirect. It relies on identifying spectral features that can be shifted. It relies on estimates of intrinsic brightness or intrinsic size. Local gravitational motions add scatter to those estimates. A galaxy can drift within a group while expansion acts in the background. This can blur the clean relationship between distance and redshift. The section returns to the journey through a void. A signal would cross mostly empty volume between two wall-like sheets. As it travels the distance it must cover slowly increases. The signal arrives with its wave crests farther apart. The energy per photon is lower. The same light that begins at a higher frequency arrives at a lower frequency. This makes distant sources harder to detect. It also makes the interior of voids feel quieter in radiation. Another visual anchor appears as a gentle close. A faint strand at the rim remains visible while the interior behind it deepens into layered darkness. The final scale shift moves from a single wave crest to the largest view. A wavelength stretches by a little across one gap. Across many gaps the stretching accumulates. Across billions of years it reshapes what can be seen. The transition remains soft. The next section lingers inside the void interior itself. Background light becomes thin there, and the emptiness takes on the calm quality of a cosmic desert. A void can feel like in a place where light forgets how to gather. The darkness deepens because illumination is diluted, stretched, and rarely redirected by matter. At this distance, the interior is not a solid black. It is a faint, even wash with long, quiet gaps. A few distant galaxies appear as soft stains. Their edges look blurred by distance, not by haze. The first unlock arrives without urgency. Emptiness does not remove light. Emptiness prevents light from building texture. 3 concepts guide this section. Dilution spreads the same light over a larger and larger area. Redshift is the stretching of light into longer wavelengths. Scattering is light diverted by thin gas and dust. Redshift receives a short definition and then returns to plain language. Redshift is the stretching of light as space expands. The rest stays visual and slow. A visual anchor opens as a corridor across the void. A faint wall sits far ahead as a pale arc. The arc is made of many weak sources layered along a sheet. Between the near rim and the far rim, the interior looks clean. It holds almost no intermediate layers. The clean line of sight makes the far arc appear sharper than expected. The payoff is immediate. The void does not brighten the far wall. The void removes foreground clutter so the wall stands out by contrast. Dilution explains why the interior remains dim even when light passes through it. Light behaves as a spreading sphere. The farther it travels, the thinner it becomes. In a richer region, scattered gas can redirect a little of that light into a soft glow. In a void, there is too little material to do that. The interior therefore stays visually empty. Another visual anchor arrives to keep the rhythm calm. A single isolated galaxy sits near the centre as a small smudge. Around it there is no halo of companion galaxies. The surrounding field stays quiet for long stretches. The payoff follows. A void can be transparent and still look empty because transparency does not create brightness. The section anchors the quietness with one safe number. The microwave background sits at about 3 degrees above absolute zero, like the last trace of warmth in stone after a very long night. This radiation fills the void as it fills every region. It does not paint the void with visible light. It is almost perfectly uniform. The unlock is simple. The most universal glow is too smooth to outline hollows. Voids become visible mainly through the pattern of where other light is absent. A new visual anchor forms as the slow cross-section. The void looks like a shallow bowl. The rim rises gently into a thin shell. The shell is uneven. It thickens where filaments feed into it. It thins where the web is sparse. The bowl interior has a soft floor of near emptiness. The physical detail is a layered edge. Density increases in steps toward the rim. It fades toward the center without a sharp break. The payoff arrives with calm clarity. A void is a gradient, not a hole. Its darkness is a smooth change in how often matter appears. An everyday analogy holds the idea without leaning on machines or rooms. A winter sky over a wide snowfield can look strangely flat. The sky contains light, yet the surface shows little texture. Only at the tree line does shape appear. Branches and trunks catch the light and cast fine shadows. Over the open snow, light is spread evenly and shadows are rare. The reason it matters is direct. A cosmic void behaves like that open snowfield. The interior has too few structures to cast many shadows or to scatter light into a visible haze. The rim is like the tree line. It introduces edges, layers, and faint contrast. Redshift adds a second layer to the quiet. In that region, light from distant sources arrives stretched. The colour shifts toward deeper tones. The energy per photon is lower. The same source appears dimmer and redder after a longer journey. Another visual anchor arrives in the far distance. Faint galaxies near the far rim look more washed out than similar ones near the near rim. Their light has travelled longer through expanding space. The payoff follows. A void is not only sparse in matter. A void is also a corridor where older, more stretched light dominates what arrives. A scale shift moves from small to immense without strain. In a small region, the change in brightness is hard to notice. In a vast region, dilution and redshift accumulate. The interior becomes a wide volume where contrast is rare. The rim becomes the main place where light is reshaped into visible structure. A limit of intuition enters softly. Intuition expects darkness to mean obstruction like a thick fog. Voids are the opposite. They are so transparent that almost nothing blocks light. Yet transparency does not create brightness. Transparency can create emptiness of texture. The limit of observation follows with a clear boundary. The interior glow is too faint to measure as a detailed map of density. Isolated galaxies are too few to sample the bowl evenly. Thin gas emits too weakly to reveal its layers directly. Indirect signs are used instead. Background light can appear slightly dimmer through the center than through the rim. The distribution of galaxies can outline the shell while missing fine tendrils. Those signs have limits of resolution. Small variations can be lost in smoothness. Large variations can be biased by where the brightest objects happen to sit. The payoff is calm and grounded. The broad truth is reliable while the fine interior texture remains softer. A final visual anchor settles the section into stillness. The rim appears as a faint ring in projection. Inside the ring, the field looks quieter and more uniform. Outside the ring, faint points become slightly more common. The ring is not a solid border. It is the place where lines of sight pass through more of the web. The payoff arrives as a soft conclusion. Emptiness becomes visible because the web is thin and uneven and because light is diluted and stretched across expanding space. The transition stays gentle. The next section approaches a farther boundary where expansion limits what any signal can ever reach. That limit gives emptiness a sharper meaning without adding urgency. A boundary can exist without a wall and still separate what can be seen from what cannot. The cosmic horizon is the quiet limit where expansion and time decide which signals ever arrive. At this distance, the web fades into a soft veil. Filaments grow thinner and more crowded together on the sky. Their details blur into a pale texture. The first unlock is simple and steady. The universe contains regions that are real, yet forever unreachable in practice. 3 concepts guide this section. The horizon is the farthest distance from which light can reach a given region. Look-back time is the time light spends travelling before it arrives. Redshift is the stretching of light as space expands. One term receives a short definition and then returns to plain language. Look-back time is the time light spends travelling before it arrives. The rest stays calm. A visual anchor forms as a dim arc at the edge of visibility. The arc is not a physical shell. It is a boundary in information. The arc appears where distant galaxies fade into the background. Their light becomes too stretched and too thin to register as distinct points. The physical detail is a gradient edge. Brightness falls with distance. It also falls as wavelengths lengthen. The boundary is therefore soft. It is more like a shoreline of mist than a cliff. The payoff arrives immediately. The horizon is not a place that blocks light. The horizon is a distance beyond which light has not had enough time to arrive. A signal would travel at light speed. Space stretches beneath it. The path length grows as the signal moves. If expansion is strong enough, the signal can lose ground in a quiet way. It still moves forward locally. The destination recedes at the same time. Another visual anchor arrives as the scene deepens. A faint filament crosses the field and then dissolves into grain. The grain is not noise in the void itself. The grain is the limit of distinguishable structure at enormous distances. The payoff follows. The farthest structures do not disappear because they stop existing. They disappear because their light becomes too sparse and too shifted to stand out. One safe number anchors the scale of time. The oldest light that can be seen comes from about 13.5 billion years ago. Like a message sent near the beginning and arriving after a nearly entire cosmic lifetime. The comparison stays gentle. The point is duration. The horizon is built from time. Time is the first ingredient. Expansion is the second. Redshift is the third. Another scene slows down to show the mechanism. Light behaves as a wave train. Each crest is separated by a certain distance. As space expands, the separation between crests increases. The wave becomes longer, the energy per photon declines. The same beam also spreads out. It covers a larger area. Both effects dim the source. The physical detail is the stretching itself. A spectrum that once had crisp features becomes shifted toward lower frequencies. The features remain ordered. They simply slide. The payoff arrives. Redshift acts like a gentle thinning of contrast. Distant objects become harder to pick out against any background. The section moves through a checkpoint that clarifies the horizon. The horizon is not the same as the edge of the observable map at any moment. The observable map is a snapshot limited by current sensitivity and current wavelengths. The horizon is a deeper physical limit set by the finite age of the universe. Even with perfect detectors, a boundary still exists. Light cannot arrive from places that have had no time to send it. Another visual anchor keeps the rhythm steady. The sky becomes a layered stack of shells. Nearby shells show sharp points and clear gaps. Far shells show smeared points and fewer distinct shapes. The farthest shell becomes a smooth surface of faint radiation. The payoff is immediate. Looking farther is looking earlier. Looking earlier is looking into a denser and simpler state. This is where emptiness gains a new meaning. At late times, space becomes emptier in volume. At early times, matter is more uniform. The horizon links both pictures. It shows how the universe changes from smoothness to web. Another scale shift arrives softly. A small candle flame seen across a valley still looks like a point. Across a continent, the same flame would vanish into darkness. In cosmic space, distance is larger than any landscape. Light can be diluted beyond recognition. At the same time, the source can still exist. The boundary is set by reach, not by existence. A limit of intuition enters. Intuition expects a line that separates visible from invisible. The real boundary is time-dependent and direction-dependent in detail. It is shaped by expansion history. It is also shaped by the fact that light must travel through a changing space. The boundary therefore feels like a moving surface rather than a fixed fence. The limit of observation follows with clear naming. Horizons are inferred from models of expansion and from measurements of redshift. Those measurements have uncertainty. Spectral features can be faint. Distances can be estimated in different ways and disagree by small amounts. Small disagreement matters when tracing a boundary across billions of light years. Another limit follows. Some distant signals are shifted into wavelengths that are hard to separate from background emission. The result is a practical horizon that depends on the band being used. The payoff remains calm. The existence of a horizon is robust. The exact contour of what is observable is less sharp. The section returns to the emptiness theme with a visual anchor that holds still. A wide void sits beneath the horizon, like a dark lake beneath a pale sky. The lake is the local emptiness. The pale sky is the farthest background. Between them, the web is a thin lace. The payoff arrives as a gentle closure. Emptiness is not only the absence of nearby matter. Emptiness is also the separation created by time and expansion. A region can be part of the same universe and still be beyond reach in any practical sense. The transition remains soft. The next section turns to a quieter force tied to space itself. It acts like a steady pressure. It makes the horizon feel more final as time passes. In the widest quiet regions, the strongest push comes from something that cannot be seen. Dark energy becomes most influential where matter is sparse, so emptiness expands more easily than crowded space. At this distance, a void looks like a broad basin with a low rim. The rim is traced by faint filaments. The interior holds long stretches of near nothing. The first unlock is calm. The emptier the region, the less gravity resists the stretch of space. Only 3 concepts guide this section. Dark energy is a uniform energy density tied to space itself. Accelerated expansion is the speeding up of the rate at which distances grow. Contrast growth is the increasing difference between dense walls and empty basins. One term receives a short definition and then returns to plain language. Dark energy is a uniform energy density tied to space itself. In that region, it does not clump into knots and filaments. It stays smooth while matter gathers into the web. A visual anchor settles in. A wide hollow opens between 2 pale walls. The walls are sheets of galaxies and thin gas. They look like soft cliffs made of haze. Over long time, the walls drift farther apart. The basin between them widens. The physical detail is gentle and specific. The wall has layering. Density rises across it like a slow slope. The interior falls away into a flatter floor. The payoff follows the image. A smooth component in the universe pushes most effectively where there is least pull. Matter provides pull through gravity. A void has less matter. A void therefore offers less resistance. The stretch of space becomes slightly more dominant there. Another visual anchor arrives as a calm checkpoint. Filaments on the rim appear thinner than expected. They look like pencil lines on a dark surface. The interior looks like clean paper with almost no markings. The payoff is immediate. Dark energy does not create the web. Dark energy amplifies the spacing between the strands once the web exists. This is where emptiness gains a second reason. Gravity gathers matter into narrow places. Dark energy keeps the gaps wide. The 2 effects cooperate without any need for drama. A main number anchors the scale of dominance. About 7 of every 10 parts of the cosmic energy budget behaves like dark energy, like 7 stoned out of 10 in a riverbed count. The comparison is plain. The point is proportion. This smooth component outweighs matter in the overall accounting. In dense regions, matter still controls local structure. In under-dense regions, the smooth component has a clearer voice. Another payoff arrives as a quiet rule. Local knots can remain bound while the large-scale spacing accelerates. A galaxy cluster can hold its internal pattern. The voids between clusters can still widen faster with time. The section keeps the scene slow and physical. Inside a void, the boundary is not fixed. The rim moves outward as matter drains towards sheets and filaments. The interior becomes more underdense relative to the average. The gradient steepens. The basin grows broader. This is contrast growth. The walls become more contrasted with the basin. The basin becomes more contrasted with the walls. A fresh visual anchor supports the rhythm. The void floor appears like a smooth dark plane. The rim appears like a low ring ridge with uneven height. Some parts rise into a thicker wall. Some parts sag into a thinner pass. The ridge is not rigid. It is a preference in where matter is found. The payoff follows. The universe becomes more web-like with time even as everything spreads apart. Spreading does not erase pattern. Spreading can sharpen pattern by emptying the basins further. A gentle analogy carries the idea without repeating earlier images. Consider a landscape after a light snowfall. A thin uniform frost coats everything at dawn. As the day warms, thicker snow, in shaded hollows, persists. Thin frost on exposed ground remains as a faint sheen. The sheen is subtle at first. When other coverings thin away, the sheen becomes the dominant surface. Dark energy plays the role of that persistent background. Matter is the thicker snow that gathers into hollows and ridges. As matter becomes more concentrated into the web, the smooth background becomes relatively more important in the empty volume. The reason it matters is immediate. Emptiness is not only leftover space. Emptiness is where the smooth component sets the pace. A scale shift arrives without strain. On short spans, the widening of a void is too small to notice. On billion-year spans, the widening becomes part of the map itself. The void diameter can grow relative to nearby structures. The rim can appear to retreat. The interior can appear to become cleaner. The visual effect is a slow clearing and widening, not a sudden change. Another visual anchor arrives to keep the cadence steady. Light behaves as a set of faint threads crossing the void. The threads are lines of sight. Each thread passes through less and less matter as the void deepens. The background sources at the far wall appear more isolated. The wall itself looks more detached from its neighbours. The payoff is quiet. Dark energy increases isolation by making distance grow faster than signals can comfortably cross. This links back to the horizon. A horizon becomes more restrictive as accelerated expansion persists. Another checkpoint touches the limit of intuition. Intuition expects a push to come from something concentrated like a wind in a valley. Dark energy does not concentrate. It is almost uniform. It acts through the structure of space rather than through streams of material. This is why it feels strange. A second intuition limit follows. Intuition expects emptiness to reduce effects. In this case, emptiness increases the effect of the smooth component. Less matter means less gravitational braking. The result is a gentle runaway in underdense regions. The section now names a limit of observation clearly. Dark energy is not measured by direct sampling of a substance. It is inferred from how distances change with time. That inference uses light from distant sources and the pattern of the web. The method has limits. Distance indicators can have systematic offsets. Redshift measurements can be precise while distances remain less certain. Large-scale patterns can be affected by cosmic variance. One region can look slightly different from another by chance. Those limits blur the exact strength and time behavior of dark energy. The payoff remains steady. The broad conclusion is robust. Expansion accelerates at late times. A smooth component consistent with dark energy explains that behavior. Another visual anchor settles the section toward its close. A vast void is seen in projection as a dark oval. Around it, a faint necklace of filaments and sheets traces an uneven loop. The loop looks thinner on one side and thicker on the other. The interior looks calm and almost featureless. Over a long time, the oval grows a little larger in commoving sense. The rim grows more contrasted. The payoff arrives as a final unlock. Dark energy makes emptiness self-reinforcing in the sense of contrast. It does not erase matter. It helps matter remain confined to the web while the basins widen. The transition stays soft. The next section follows a subtle imprint of voids on ancient background light where a tiny energy change reveals the void path without any sharp signal. A void can leave a mark on ancient light without glowing at all. The mark appears because gravity changes, while background light crosses the emptiest basins. At this distance, the oldest background is a smooth dome with faint mottling. The mottling is gentle. It is nearly uniform. The first unlock is quiet. The emptiest regions can imprint the background only when expansion makes gravity evolve. Only 3 concepts guide this section. The background radiation is the universe's oldest widespread light. Gravitational potential is the depth of a gravity hill or valley. The integrated gravity shift is a tiny energy change during a long crossing. One term receives a short definition and then returns to plain language. Gravitational potential is the depth of a gravity hill or valley. In denser regions, the valley is deeper. In emptier regions, the valley is shallow. The visual anchor opens on a broad void seen in 3 dimensions. Its rim is a low ring of faint filaments. The interior is a clean basin. The basin has a gentle density gradient toward the center. A thread of background light crosses the basin. It does not bounce. It does not scatter much. It simply passes through. The payoff arrives immediately. If the gravity landscape stayed perfectly fixed, the light would leave with the same energy it had on entry. The descent would be balanced by the climb. In a universe with late time acceleration, the landscape changes while the light is in transit. A gravity hill can flatten slightly. A gravity valley can become less deep. The balance becomes imperfect. The light exits with a tiny mismatch. In an underdense region, the mismatch tends to be a slight loss. The background looks a little cooler in that direction. The physical detail is a shallow slope that changes while the crossing happens. Another visual anchor steadies the rhythm. The rim of the void appears as a thin shell. The shell is uneven. It thickens where filaments merge. It thins where the web is sparse. Behind the shell, the interior looks smooth. It is not featureless. It is simply faint. The payoff follows. The rim outlines where matter sits. The interior outlines where matter does not sit. The background light is sensitive to both when gravity changes with time. The effect is small because the background is already smooth. The effect is also small because the gravity in a void is weak. One safe number anchors the scale of the imprint. The temperature shift is only a few millionths of a degree, like the faint warmth difference across a long shadow on a cool rock. The comparison stays natural. The point is subtlety. This is not a bright signature. It is a gentle bias spread across a large patch of sky. Another payoff arrives in plain language. The void does not shine on the background. The void slightly drains energy from the background light as the gravity field relaxes. The section keeps the path calm. Light behaves as a long wave train. Each crest stretches as the universe expands. That stretching is already present everywhere. The integrated gravity shift is an extra and tiny adjustment layered on top. It appears only because the gravity landscape evolves. A visual anchor returns to the microwave dome. A faint, cool oval sits against the mottled field. The oval is broad, its edge is soft. It matches the sky projection of a known underdense basin. The oval is not a sharp stamp. It is more like a shallow dimple in a smooth surface. The payoff follows. A single void cannot be confirmed by the one cool patch alone. Many features overlap. Many basins and ridges sit along any line of sight. The signature is therefore statistical. It becomes clearer when similar voids are combined. Their patches are aligned and averaged. The combined imprint can rise above the background mottling. A scale shift arrives without strain. In a small region of sky, the background looks like random speckle. In a large region, patterns emerge as gentle gradients and broad ovals. Over long time, expansion makes gravity relax in underdense space. That long time is what the crossing samples. The crossing itself is not a moment. It is a journey through evolving geometry. Another visual anchor keeps the cadence steady. A photon enters the void near the rim. The rim is a slight gravity ridge. The photon gains a little energy as it falls inward. The interior is a shallow basin. While the photon travels, the basin relaxes. The depth becomes slightly less. On the way out, the climb returns a little less energy than the fall gained. The photon exits with a slight deficit. The payoff is immediate. The imprint is not a local property of the void alone. It is a property of the void plus cosmic history. If expansion did not accelerate, the imprint would be far smaller. If the gravity landscape did not change, the imprint would cancel away. The section now touches the limit of intuition. Intuition expects gravity effects to be dramatic near dense objects. Here the effect comes from weak gravity integrated over huge distance. The mind expects a strong push for a measurable result. The reality is the opposite. A tiny bias repeated across millions of light years can become a measurable pattern. Another payoff arrives in calm language. Emptiness becomes a measuring stick because it offers a long path with little clutter. The integrated shift accumulates quietly over that path. The section names a clear limit of observation. The imprint is so small that a single sky patch cannot confirm it cleanly. The background mottling itself has natural variation. That variation is larger than the void imprint on many scales. Foreground emission can also add confusion. Dust and gas in the nearer universe can add their own patterns. Another limit follows. Void catalogues are imperfect. The distribution of galaxies is sparse in under-dense regions by definition. This makes the void boundary uncertain. A void can look larger or smaller depending on sampling. Distance estimates can smear a rim into a thicker wall. Those uncertainties blur any expected imprint. The payoff remains grounded. The existence of a small integrated imprint is consistent with a universe where acceleration alters gravity over time. The exact strength for any one void is not sharp. The best evidence comes from careful averaging across many basins and from comparing different selections. Another visual anchor arrives as a soft closing image. A chain of voids lies between brighter nodes. Each void projects as a broad dim oval on the sky. Their rims form faint arcs. Across those arcs, the background mottling shifts by tiny amounts. The shifts are not visible as a picture in ordinary light. They exist as a gentle texture in the oldest radiation. The payoff settles the section. The background carries the memory of emptiness, not as a map of objects, but as a record of how gravity evolves in the largest hollows. The transition stays soft. The next section follows how redshift stretches light so far that signals thin into silence and distant structure fades from view. Some signals fade not because they weaken at the source, but because the universe stretches them into quietness. Redshift can thin light until it slips below practical notice, leaving distant structure present yet effectively silent. At this distance, a far filament looks like a soft smear rather than a line. The smear has no sharp edge. It dissolves into the background. The first unlock is calm. Distance becomes invisibility when wavelength and brightness drift together for long enough. Only 3 concepts guide this section. Redshift is the stretching of light into longer wavelengths. Surface brightness dimming is the loss of apparent brightness spread across an image. The observational window is the limited set of wavelengths that can be separated from background. One term receives a short definition and then returns to plain language. Surface brightness dimming is the fading of light per apparent area. The rest stays slow and visual. A visual anchor opens on a faint galaxy near the far rim of a void. Its glow is not point-like, it has a soft disk. The disk has a gentle radial gradient. It brightens toward the center. It fades toward the edge. The edge is where the story begins. The outer parts of the disk are the first to vanish. The center remains longer. The payoff arrives immediately. distant structure disappears from the outside inward, not all at once. Redshift stretches the emitted light. What begins as shorter wavelength light arrives longer. At the same time, the image spreads over a larger apparent area because of geometry. The same photons are shared across more sky. The disk therefore fades faster than intuition expects. Another visual anchor keeps the rhythm steady. A filament beyond the galaxy is traced by a few sparse points. Between points there is darkness. The darkness is not empty of space, it is empty of detected photons. The payoff follows. The web can be present yet undrawn because the ink of photons is too thin. One safe number anchors the scale of stretching. A far source can arrive with its wavelength stretched by a factor of 10, like a spring pulled from a tight coil into a long, gentle loop. The comparison stays simple. The point is that the same pattern becomes longer and less energetic. The effect is not only colour change, it is energy thinning. Another payoff arrives in plain language. When wavelength stretches, the energy per photon drops. When energy drops, the same stream of photons is harder to separate from background. The observational window becomes a gate. A window is a band of wavelengths where background is low enough and contrast is possible. Outside that band, the source can be buried. A visual anchor appears as a layered curtain of faint glow. Near sources show crisp shapes. Far sources show softened shapes. Beyond a certain distance, only the brightest cores remain as points. Disks and faint halos become invisible. The payoff follows. The universe can look emptier than it is because faint extended light is the first to vanish. This matters for voids and horizons. It matters because the web is mostly faint extension. The brightest nodes are rare, the filaments are thin, the sheets are delicate. When faint extension disappears, the map becomes biased toward knots. The emptiness appears deeper. The scale shift arrives softly. On the scale of a single galaxy, a fading disk looks like a shrinking island of light. On the scale of hundreds of millions of light years, the same fading removes whole filaments from view. The pattern of the web changes in appearance without changing in reality. Another visual anchor maintains the cadence. A far sheet is seen edge-on as a pale band. The band has thickness. It has a slow brightness gradient across its width. With distance, the band becomes narrower and fainter. Its thickness is lost first. Its edges blur into the background. The payoff arrives. Large-scale structure does not only recede, it loses dimensionality and appearance. Sheets become lines, lines become points, points become absent. The section now touches a limit of intuition. Intuition expects brightness to fall mainly with distance squared. That is true for point sources in simple settings. Extended sources suffer extra dimming because of cosmic expansion. Time dilation spreads arrival times. Wavelength stretching lowers photon energy. The image also covers a larger apparent area in a particular way. These effects stack. The result is that faint surface brightness drops steeply. The mind often underestimates this. Another payoff arrives, gently correcting the picture. The universe is not merely far. The universe is also diluted in every channel that carries information. The section names a clear limit of observation. Detection depends on thresholds. Background noise sets those thresholds. In some wavelength bands, background emission is high. In others, it is low. A source can be visible in one band and invisible in another. The band choice shapes the map of the distant universe. Another limit follows. Dust and gas along a line of sight can add their own glow. That glow can mask faint extended structure. The void interior is cleaner, yet the signal is also weaker because sources are rare. Sampling becomes uneven. A filament can be missed because it has too few bright traces. A sheet can be missed because its light is too spread out. The payoff remains calm. Absence in an image is not always absence in space. It can be absence in the observational window. A new analogy holds the idea without repeating earlier ones. Consider ink on wet paper. A crisp dot spreads into a pale blot. The ink has not left the page. It has spread. The contrast drops. The shape becomes hard to distinguish from the paper tone. Redshift and surface brightness dimming act like that spreading. The information remains, yet its contrast against background falls. The reason it matters is direct. Distant structure can become effectively silent even while it exists. Another visual anchor prepares the close. The rim of a void is traced by a necklace of brighter galaxies. Beyond it, the far wall becomes a faint haze with few distinct points. The void itself looks like a widening basin of black. The payoff settles the section. The universe appears empty partly because expansion turns light into long, thin waves. Those waves slip beneath practical separation from background. The transition stays soft. The next section moves from light to mass that does not shine. The invisible scaffolding of dark matter sets the web's shape and emptiness follows its hidden contours. The web looks delicate in light, yet its strongest scaffolding is invisible. Dark matter shapes the valleys and ridges of gravity, and ordinary matter mostly follows those hidden contours into filaments and nodes. At this distance, a filament appears as a faint chain of small galaxies. Between those points lies darkness. The first unlock is calm. The emptiness between bright points is not empty of gravity. Only 3 concepts guide this section. Dark matter is mass that interacts mainly through gravity. Gravitational lensing is the bending of light by mass. The halo is a roughly round cloud of dark matter around a galaxy or cluster. One term receives a short definition and then returns to plain language. Gravitational lensing is the bending of light by mass. The rest stays slow and visual. A visual anchor opens on a distant cluster at the edge of a void. The cluster is not described by bright glare. It is described by geometry. Background galaxies behind it appear slightly stretched. Their shapes become gentle arcs. The arcs curve around an unseen center. The physical detail is a ring-like distortion in the faint background. The payoff arrives immediately. Mass can be mapped without seeing it shine because light records the curvature of space it crosses. The arcs are not a decoration. They are a trace. They point to a hidden concentration. The hidden concentration is mostly dark matter. Ordinary matter settles into the same potential well, then cools and forms luminous structure. Another visual anchor arrives to keep the rhythm steady. Along a filament galaxy, groups appear like dim knots. Around each knot lies a dark halo. The halo is not a hard shell. It is the density profile that fades outward. The profile is steeper near the center. It is shallower farther out. The payoff follows. Halos overlap in filaments. Their overlap makes a ridge in gravity. Ordinary gas drifts toward that ridge. It compresses slightly near the ridge. It becomes more likely to form stars in the densest pockets. The filament therefore shines faintly. The filament shines only where the dark scaffold has already shaped the flow. One safe number anchors the proportion. About 5 of every 6 parts of matter is dark matter, like 5 stones out of 6 that cannot be seen beneath a clear stream. The comparison stays natural. The point is dominance. The visible part is the smaller share. The invisible part sets most of the gravity. Another payoff arrives in plain language. The universe looks empty because the visible part is sparse. The gravity landscape is less sparse. It is smoother and more extended. A void is not a region with no dark matter. A void is a region with far less dark matter than average. The same is true for gas and stars. The difference is that dark matter sets the first map and ordinary matter draws the visible ink on top. A scale shift arrives softly. Inside a single galaxy, dark matter explains why outer stars can orbit fast without enough visible mass. On the scale of a filament, dark matter explains why galaxies line up along long ridges. On the scale of voids, dark matter explains why basins remain wide and why rims become walls. The shift is gentle and steady. Another visual anchor holds the void boundary. The rim of the void appears as a sheet. Along the sheet, lensing distortion in the background becomes slightly stronger than in the interior. The sheet is not bright. It is a gravity contour traced by subtle stretching. The payoff follows. A void can be outlined by how it fails to bend light as much as its surroundings. Less mass means weaker lensing. The interior therefore leaves background shapes closer to their original forms. The rim introduces gentle shearing. The edge becomes visible as a change in distortion pattern even when light is scarce. Another analogy carries the idea without repeating earlier ones. Imagine a thin elastic fabric with shallow dimples and ridges. A marble rolling across the fabric drifts toward ridges if the ridges are long and connected. It can wander in a basin if the basin is broad and shallow. The marble represents ordinary matter. The fabric is the gravity field mostly set by dark matter. The reason it matters is immediate. Emptiness in the visible universe is partly a map of where the fabric is low. The section touches a limit of intuition. Intuition expects emptiness to mean a lack of influence. Yet gravity extends far beyond visible boundaries. A halo does not stop where light stops. It fades gradually. Its reach can overlap with neighbours. This makes the web more connected than a light-based map suggests. Another payoff arrives. A void is not a hole punched into the gravity field. It is a gently rising bowl. The rim is a gentle ridge. The ridge is composed of overlapping halos and sheets. The bowl is composed of fewer halos. The shape is continuous. The section now names a limit of observation clearly. Dark matter cannot be detected by emitted light because it does not radiate. It is inferred through its gravitational effects. Lensing measurements rely on averaging many faint galaxy shapes. Individual shapes have intrinsic variety. That variety adds noise. The lensing signal is small for many structures. It becomes clearer only by combining many lines of sight. Another limit follows. Mapping halos requires assumptions about geometry. A spherical halo model is an approximation. Real halos can be slightly stretched. They can be clumpy, they can be aligned with filaments. Those details are hard to resolve. The result is a map that is reliable in broad form and softer in fine grain. The payoff remains calm. The hidden scaffold is traced as a probability field rather than as a crisp object list. Another visual anchor settles the section toward its close. A wide filament crosses the sky as a faint band of points. Behind it, the background galaxies show slight tangential stretching. The stretching changes smoothly across the band. It fades away toward the void interior. The physical detail is a sheer gradient. It is strongest near the band. It weakens with distance from the band. The payoff arrives as a final unlock. The universe is empty in light because visible matter is clumpy and rare. The universe is less empty in gravity because dark matter fills the web with extended halos and long ridges. Voids remain the largest volumes because even the dark scaffold is thin there. The transition stays soft. The next section turns from scaffolding to destiny, where usable energy spreads thinner over time and structure becomes harder to maintain in an ever-emptier volume. A quiet future can be written into the present by the way energy spreads. Entropy increases as the universe expands and usable differences in heat and density become thinner across the vast empty volume. At this distance, a bright cluster sits like a small island at the edge of a void. Around it, darkness dominates. The first unlock is gentle. The universe does not need to lose energy to feel colder and emptier. It only needs energy to become less usable. Only 3 concepts guide this section. Entropy is the measure of how spread out energy becomes. Gradient is a difference in temperature or density across space. Heat death is the approach toward a uniform low gradient state. One term receives a short definition and then returns to plain language. Entropy is the measure of how spread out energy becomes. The rest stays calm and visual. A visual anchor opens on a thin glow of gas near a filament. The glow fades as distance from the filament increases. The physical detail is a temperature gradient. Gas near the filament is warmer and denser. Gas in the void interior is cooler and thinner. The gradient is a source of change. It can drive flows and radiation. The payoff arrives immediately. Structure persists because gradients exist. When gradients shrink, change slows. A second visual anchor arrives to keep the rhythm steady. A wide void floor appears like a dark plane. Above it, faint background radiation forms a smooth dome. The dome has very slight mottling. The mottling is subtle. The payoff follows. Even a nearly uniform background still contains a small difference between hot and cold. That difference powers the slow movement of energy from concentrated places to diffuse places. Over time, the movement reduces contrast. It does not erase matter, it erases sharpness. One safe number anchors the scale of cooling background. The background radiation is about 3 degrees above absolute zero, like a cellar that stays just barely warmer than deep winter air. The comparison stays simple. The point is that the baseline is already low. The universe begins its late story from a cold starting point. Any remaining gradients are precious. Another payoff arrives. As expansion continues, the background temperature falls. As it falls, even faint processes become harder to sustain. Radiation becomes longer wavelength. It carries less energy per photon. The empty volume becomes a quieter reservoir. The section moves through a checkpoint that ties entropy to emptiness. Entropy increases when energy spreads into more available space. Expansion increases available space. Voids provide huge volume with little obstruction. Energy that leaks into voids rarely returns to concentrate again. The basin acts like a sink for gradients. The physical detail appears in radiation fields. A filament emits more infrared light than a void interior. Over time, that light crosses into the void and spreads. The difference between filament and void therefore softens. Another visual anchor supports the rhythm. A sheet at the edge of a void appears as a pale curtain. The curtain has ripples. Behind it, the interior is smooth. The ripple contrast decreases over long time as radiation and gas flows reduce differences. The payoff follows. The universe becomes emptier in the sense of contrast. Not all matter leaves. The ability of matter to stand out decreases. A gentle analogy carries the idea without repeating earlier images. Consider perfume released in still air. Near the source, scent is strong. Far away, scent is weak. Over time, the scent spreads. The room becomes more uniform. The total amount of perfume does not vanish. The difference between near and far vanishes. The reason it matters is immediate. Entropy makes the universe more uniform in its energy distribution. The emptiness feels deeper because fewer sharp differences remain to mark where structure is. A scale shift arrives softly. In a small box, mixing can happen quickly. In cosmic space, mixing is slow. It can take billions of years for energy to spread across huge distances. Yet the direction is the same. The cosmos moves from sharp differences toward broad uniformity. The section now links gradients to the engine of structure. Stars form where gas can cool and collapse. Cooling requires radiating energy away. Radiating energy away increases entropy. It spreads energy into space as light. This connects local structure to global emptiness. Each act of structure building creates more diffuse radiation in the background. The payoff is quiet. The universe builds islands by paying with a wider ocean of low-quality energy. Another visual anchor arrives to keep cadence steady. A galaxy cluster is surrounded by a faint halo of hot gas. The halo has a density profile that fades outward. Its edge is not sharp. It is a long tail into the void. The tail is where energy leaks away as radiation. The physical detail is a boundary layer where density and temperature fall together. The payoff follows. Boundaries are where gradients live. Boundaries are also where gradients erode. A limit of intuition enters softly. Intuition expects entropy to mean disorder in a messy sense. In cosmic space, entropy can increase while structures remain crisp locally. A cluster can be well formed while the overall background becomes more uniform. Entropy is about energy dispersal, not about visible chaos. Another limit follows and names what breaks down in observation. The entropy of the whole universe cannot be measured directly as a single number. Many components contribute. Radiation gas, dark matter, and compact objects each carry entropy in different ways. Some parts are hard to count. Some parts are inferred rather than observed. The result is uncertainty about the detailed budget. The broad trend remains reliable. Gradients decrease as expansion increases volume and as radiation spreads energy outward. The payoff stays grounded. The future can be described without exact bookkeeping. Uniformity increases, contrast decreases, the empty volume becomes the main reservoir. Another visual anchor prepares the close. A faint filament is seen against a vast void. The filament still glows, but its outer haze is thinner than before. The void interior is darker and smoother. The difference between wall and basin remains, yet the fine texture softens. The payoff arrives as a final unlock. Emptiness is not only a matter distribution. Emptiness is also an energy landscape. As entropy rises, usable differences fade. The universe trends toward a quiet equilibrium where few gradients remain to mark structure. The transition stays gentle. The next section follows how star formation declines as fuel becomes locked away, and the bright era narrows into a long dusk without any sharp end. A bright era can end quietly not with an event, but with a thinning of fuel. Star formation declines as cold gas becomes scarce in the widest empty volumes and becomes locked into existing structures. At this distance, a filament looks like a faint chain with long gaps. The gaps grow larger in the emptier regions. The first unlock is calm. The universe becomes darker mostly because new lights become rarer, not because old lights vanish all at once. Only 3 concepts guide this section. Star formation is the conversion of cold gas into stars. Gas depletion is the gradual loss of available cold gas. Isolation is the growing separation between bound islands as expansion accelerates. One term receives a short definition and then returns to plain language. Gas depletion is the gradual loss of available cold gas. The rest stays visual and slow. A visual anchor opens on a spiral-shaped glow at the edge of a void. Its outer disk is faint. Its inner region is brighter. Around it, the void interior is quiet. The physical detail is a thin disk with a radial brightness gradient. The disk looks like a pale lens. Its outer edge is soft and nearly transparent. The payoff arrives immediately. New stars prefer dense cold pockets. Voids offer very few such pockets. Most cold gas drifts toward filaments and nodes long before it can condense in a basin. The void therefore becomes a place of long waiting. Another visual anchor keeps the rhythm steady. A sheet at the rim of the void looks like a dim curtain. Along the curtain, small clumps appear as beads. Between beads there is faint haze. The payoff follows. Star formation does not happen everywhere inside a sheet. It happens where the sheet wrinkles into denser knots. Those knots are rare compared with the volume of the void. As acceleration continues, the void volume grows faster than the number of new knots. The share of space that can make new stars therefore shrinks. One safe number anchors the timescale of decline. In about a few tens of billions of years, like several long chapters stacked end to end, most fresh star formation becomes a faint trickle compared with the earlier peak. The comparison stays gentle. The point is not an abrupt stop, the point is a long taper. Another payoff arrives in plain language. A taper changes what the universe looks like. Bright new blue stars become rarer. The average light becomes redder and dimmer. The sky of distant structure becomes less crowded with fresh points. The emptiness gains a new tone. It is not only empty of matter, it is empty of ongoing creation. A scale shift arrives softly. In a single galaxy, gas can cycle between warm and cold phases. Some gas can cool and collapse, some can be heated and dispersed. Over billions of years, the net reservoir declines. Over a larger region, filaments feed nodes less effectively. As expansion stretches distances, the supply lines become longer and thinner. The flow of gas into dense regions becomes slower. The web remains, yet its growth slows. Another visual anchor appears to keep the cadence steady. A long filament is seen in projection as a faint band. Near its center, a node is slightly brighter. The band itself becomes patchier with distance. The patchiness is not noise, it is the map of where gas remains dense enough to form stars. The payoff follows. The web becomes more skeletal with time. Nodes remain. The thin connecting strands grow fainter in their light output. The voids between strands become more dominant in the visible map. The section now ties isolation to the decline. Accelerated expansion increases separation between unbound regions. Gas that sits in the void is less likely to fall into a distant filament as time passes. The basin becomes more cut off. Local gravity can still pull gas toward the nearest ridge. It struggles to pull gas across the widening gap toward farther ridges. The payoff arrives. Isolation turns the web into a set of separate islands. Each island consumes and rearranges its local supply. The empty ocean between islands grows. The section introduces a gentle analogy without repeating earlier ones. Consider a river delta in a long drought. The main channels still exist. Water still moves, yet the side channels dry. New deposits become rare. The landscape keeps its shape while its activity slows. The reason it matters is immediate. Star formation is activity. When fuel thins and channels lengthen, activity becomes localized and reduced. The universe keeps its web, but the web glows less. Another visual anchor returns to the void rim. The rim is a low ring of faint structures. The ring has gaps. The gaps look wider than before, the interior looks smoother. The physical detail is a widening separation between the rim segments like a necklace with longer stretches of string between beads. The payoff follows. The appearance of emptiness increases even if the mass distribution changes only gradually. Light is a biased tracer. When star formation slows, light concentrates into fewer places. Many regions become effectively dark even while containing gas and dark matter. A limit of intuition enters softly. Intuition expects a universe that expands to also mix and smooth. Here, expansion can increase separation while local bound systems remain stable. A galaxy can keep orbiting stars while the space between galaxies grows. The decline in new stars is not a sign of local collapse. It is a sign of diminishing supply and widening gaps. The section names a clear limit of observation. The future decline is inferred from models and from current star formation trends. Observations reach only a limited time range directly. Distant galaxies show earlier epochs. Nearby galaxies show the present. The long future is extrapolated. Those extrapolations depend on feedback processes in gas and on how gas is recycled. Those processes are complex. They vary by environment. The broad direction remains steady. Gas becomes less available. Isolation increases. Star formation declines. Another payoff arrives in calm language. The universe grows quieter because the cycle that makes bright new stars becomes less common across the largest volumes. Voids become quieter first. Filaments become quieter later. Nodes remain as long-lived embers. A final visual anchor settles the section. A cluster sits near a void edge. Its faint halo of hot gas fades outward. Beyond it, the void interior is a dark plane with rare points. The contrast between island and ocean is clear. The payoff arrives as a gentle closure. The universe becomes empty for a reason that is slow and structural. Fuel becomes locked. Supply lines thin. Expansion increases separation. The next section turns to the long isolation that follows where signals struggle to cross the growing ocean, and each island becomes a quieter system in a deeper darkness. Distance does not only hide the universe in darkness, distance can remove it from contact. The event horizon is the quiet line where expansion makes separation permanent. At this distance, a familiar knot in the web sits bright against a wide void. The knot is small compared with the surrounding darkness. The first unlock is gentle. Some regions remain real and structured, yet become forever unable to exchange signals. Only 3 concepts guide this section. The event horizon is the distance beyond which signals never arrive. Causal contact is the ability for 2 regions to influence each other. Isolation is the long-term separation of bound islands within expanding space. One term receives a short definition and then returns to plain language. The event horizon is the distance beyond which signals never arrive. In that region, the boundary is not a wall. It is a limit set by expansion history. A visual anchor opens on a vast sphere of faint background light. Across the sphere, a thin circle is imagined as a contour of reach. Inside the circle, distant galaxies still appear as points and smears. Outside the circle, nothing is visibly different in the moment. The physical detail is a boundary drawn in information rather than in matter. The payoff arrives immediately. A horizon can exist even when nothing special happens at the boundary itself. A signal would still move locally at light speed. Space stretches beneath the signal. The destination recedes. If the recession wins over long-time arrival never happens. Another visual anchor keeps the rhythm steady. A long filament runs along the rim of a void like a faint seam. The seam has knots where halos overlap. The seam has gaps where light is too thin. Beyond it, a second filament sits farther away and appears redder and dimmer. The payoff follows. The farther filament is not only harder to see, it is also closer to a limit where its future influence disappears. Light behaves as a messenger and as a tether. When the messenger takes too long, the tether weakens into irrelevance. One safe number anchors the scale of reach. The event horizon is on the order of about 16 billion light-years, like a journey that lasts 16 billion years even at light speed. The comparison is simple. The point is duration. Reach is not about courage or power. Reach is about time available before expansion stretches the path beyond completion. Another payoff arrives in plain language. A large universe can be observable without being fully connected. Observability is about light arriving from the past. Connectivity is about signals exchanged in both directions across time. The horizon speaks to the second idea. A distant galaxy can be seen from its earlier light. That galaxy can still be unable to ever receive any later influence. The view and the handshake are different. A scale shift arrives softly. On the scale of a galaxy cluster, gravity binds matter into a stable island. Orbits persist. Halos keep their shape. On the scale of superclusters and beyond, expansion dominates. Distances between islands grow. The empty ocean between them grows faster than any bound bridge can form. Another visual anchor steadies the sense of separation. Two clusters sit on opposite sides of a broad void. A faint sheet between them is barely visible. Over long time, the sheet thins in light as star formation declines. The void widens. The clusters remain compact. The payoff follows. Local structure can remain while large-scale contact fades. Isolation is therefore not the end of structure. It is the end of shared structure across great distances. The universe becomes a set of quiet archipelagos. Each archipelago keeps internal motions. The ocean between archipelagos becomes unbridgeable for influence. A new analogy carries the idea without repeating earlier ones. Consider an echo released in a cavern that slowly grows while the sound travels. The echo expands into more space. Its energy spreads thin. The far wall drifts away. The return becomes weaker and later. Eventually the return never comes. The reason it matters is immediate. Signals in an accelerating universe behave like that echo. The signal is not blocked. The space for the signal to fill grows faster than the signal can complete the round trip. Another payoff arrives as a small clarity. The horizon does not mean light stops moving. It means the list of reachable places shrinks in practical terms. It also means that the future sky simplifies. Distant galaxies that are now visible can fade and slip beyond reach. Their light stretches to longer wavelengths. Their arrival rate slows. Their last photons become spaced farther apart in time. Another visual anchor keeps the cadence steady. A distant galaxy appears as a faint oval with a soft edge. The oval becomes dimmer as its light stretches. The edge fades first. The central glow persists longer. The physical detail is a shrinking of visible structure toward the core. The payoff follows. Even before the horizon matters for causality, redshift matters for visibility. The sky can become empty in two layered ways. It can become empty because light grows too thin to detect. It can become empty because later light never arrives at all. The section now touches a limit of intuition. Intuition expects the future to resemble the past with slower motion. In an accelerating universe, the future is different in kind. The horizon makes the accessible region approach a fixed volume in a broad sense. Beyond that, more space exists, yet it stops contributing new information. The mind expects more space to mean more connection. Here, more space can mean more separation. Another payoff arrives calmly. The horizon turns expansion into an asymmetry. Earlier light can arrive from far away. Later influence cannot be sent back. The past remains visible while the future becomes one-sided. This is a quiet reason the universe can feel unsettling. The view is wide, the touch is limited. The section names a clear limit of observation. The event horizon is not observed by watching signals fail to arrive from the future. It is inferred from the measured expansion history. That history comes from distance indicators and from patterns in large-scale structure. Those measurements carry uncertainty. Small changes in expansion parameters change the exact horizon distance. Another limit follows. The horizon is a global concept. Local environments vary. Voids and filaments create small variations in gravitational potential that shift photon paths slightly. Those variations do not remove the horizon. They blur the precise contour of reach by a modest amount. The payoff remains grounded. The existence of a causal boundary in an accelerating universe is robust, even if its exact radius is softened by measurement limits. Another visual anchor settles the section toward its close. The web is seen as a lace sheet draped over a dark volume. The lace has bright knots and faint threads. The volume beneath is mostly empty. A faint circle of reach is imagined on the lace. Inside knots remain connected by possible influence across long time. Outside knots still exist but become silent neighbours. The payoff arrives as a final unlock. The universe is empty for a reason that is not only distribution, it is also communication. Expansion builds distance faster than influence can cross it. This turns emptiness into a lasting feature of the future. The transition stays soft. The next section follows how time itself stretches the meaning of distance, and how the remaining islands drift toward a quieter, simpler sky, with fewer messages and fewer changes. The sky can empty without removing anything from space. It empties when time itself stretches the spacing between arriving signals until patterns dissolve into rare quiet events. At this distance, emptiness becomes a timing problem as much as the distance problem. The first unlock is gentle. A far source can remain real and luminous, yet become effectively absent because its photons arrive too slowly and too red. Only 3 concepts guide this section. Time dilation is the stretching of observed time intervals by expansion. Redshift is the stretching of light into longer wavelengths. Photon arrival rate is how often photons reach a given area. One term receives a short definition and then returns to plain language. Time dilation is the stretching of observed time intervals by expansion. The rest stays calm and visual. A visual anchor opens on a distant galaxy, seen as a faint oval. The oval has a soft edge and a brighter center. The edge fades into black. The center holds a small core of light. Around it, the background remains smooth. Light behaves as a messenger that arrives in pulses. Those pulses are not heard, they are counted by their spacing in time. The payoff arrives immediately. Distance does not only dim light, expansion also spaces the light out in time. The galaxy does not only look fainter, it also looks slower. Another visual anchor keeps the rhythm steady. A long filament appears as a chain of dim points. Between points, darkness dominates. Each point is not steady. It is a weak stream of photons stretched into longer waves. The payoff follows. When arrival times spread, the sky can lose texture even before it loses sources. A structure can persist in space while the pattern of arrivals becomes too sparse to outline it. At this distance, a signal would arrive with its features widened. A fast change at the source becomes a slower change at the receiver. A brief flare becomes a long, low glow. A sharp pulse becomes a gentle rise and fall. The same energy is shared across more time. The light becomes easier to miss. One safe number anchors the horizon of patience. Over about 100 billion years, like the span in which continents drift and reshape, many times the visible universe trends toward fewer bright new sources and slower arriving light from the farthest ones. The comparison stays natural and slow. The point is a long taper, not a sudden cut. Another payoff arrives in plain language. A far galaxy can fade in two ways at once. Its light shifts into wavelengths that blend with background. Its photons also arrive with wider gaps. The map of the cosmos becomes less about lines and more about isolated points. The section moves through a checkpoint. Redshift stretches wavelength and lowers photon energy. Time dilation stretches the time between wave crests and between emission events. Both effects reduce contrast. The physical detail appears in the galaxy's gradient. The outer disk vanishes first, the inner disk weakens next. The core persists longest. The sky therefore simplifies from a soft oval into a point. Then the point becomes a rare event. Another visual anchor arrives to keep cadence steady. The far sky is imagined as a dark basin with occasional faint specks. Each speck is not a constant lamp. It is a single photon arrival that triggers a tiny moment of detected light. The spacing between specks grows. The payoff follows. The universe can look empty because light becomes grainy in time. A source can still emit. The arrivals can still happen. Yet the arrivals can become so rare that structure is no longer drawn. A new analogy carries the idea without repeating earlier ones. Consider raindrops on a very still pond. When drops fall, often rings overlap and a pattern appears. When drops become rare, each ring spreads alone and fades before the next arrives. The pond is not drier in an instant. It is quieter between events. The reason it matters is immediate. Photon arrivals are like those drops. When they become rare, the sky loses continuous texture. The section now adds a gentle scale shift. On the scale of a single star in a galaxy, emission can be steady for long periods. On the scale of a galaxy's integrated light, the sum is usually smooth. On the scale of a horizon-shaped sky, the smooth sum breaks into fewer contributors. Distant galaxies leave the map first. Nearby bound islands remain longer. The sky becomes a local story. Another visual anchor supports the rhythm. A cluster near a void edge remains as a faint swarm of points. Its outer halo is barely visible. The halo has a soft boundary where brightness falls away. Beyond the boundary, the void interior is dark and smooth. The payoff follows. A horizon does not erase nearby islands. It reduces the number of islands that continue to add new information. The reachable set becomes more local. The reachable light becomes less varied. The section touches a limit of intuition. Intuition expects the past to be fixed and the future to be open. In an expanding universe, the past remains visible from far away, while the future influence becomes limited. The sky becomes a museum of earlier light. It is wide, yet it becomes static in its most distant parts. Another payoff arrives calmly. The sky can remain full of history while becoming empty of change. The section names a clear limit of observation. Time dilation and redshift at extreme distance push light into bands where foreground-backgrounds dominate. The faintest signals become inseparable from diffuse emission. Detection then depends on modelling and subtraction. That introduces uncertainty. Another limit follows. The far future cannot be observed directly. It is inferred from present expansion and from trends in star formation. Those trends depend on gas physics and on feedback in galaxies. Those details are complex. The broad direction remains stable. Expansion stretches time intervals for distant sources. Arrival rates thin. Contrast declines. Another visual anchor steadies the close. A distant galaxy is seen at the rim of visibility. Its oval has collapsed into a dim point. Over long time, the point becomes less frequent as an arrival pattern. The background becomes smoother. The physical detail is the loss of the outer gradient, then the loss of the inner gradient, leaving only the core. The payoff arrives as a final unlock. The universe is empty for a reason that is quietly mathematical. Expansion stretches not only space but the cadence of information. When cadence slows enough, structure stops being drawn in light. The transition stays soft. The next section turns to the last long-lived lights and to the slow cooling that follows, where the remaining islands settle into a deeper calm without sharp endings. The last lights are not dramatic. They are patient. They shine with a steady economy, using small gradients that remain when most fuel is gone. The first unlock is calm. Darkness grows because the universe keeps spending its remaining energy more slowly and more locally. Only 3 concepts guide this section. A red dwarf is a small, long-lived star. A white dwarf is a cooling stellar remnant. Cooling curve is the gradual fading of heat emission over time. One term receives a short definition and then returns to plain language. A cooling curve is the gradual fading of heat emission over time. The rest stays in slow imagery. A visual anchor opens on a dim red star sitting in a sparse field. Its light is soft. Its colour leans toward deep ember red. Around it, the background is nearly black. The physical detail is a faint halo of light that falls off smoothly with distance. The halo has no sharp edge. It fades like mist. The payoff arrives immediately. Small stars burn slowly because their cores run cooler and their fuel is consumed at a gentle pace. In the long future, these stars dominate the remaining starlight. They do not make the sky bright. They keep it from becoming fully dark too quickly. Another visual anchor keeps the rhythm steady. Nearby, a white dwarf appears as a tiny point with a pale glow. It has no surrounding halo like a large star. Its light is tight and crisp. The payoff follows. A white dwarf does not generate new energy by fusion. It glows from stored heat. Its fading is therefore a slow release. The universe becomes empty not because objects disappear, but because their emissions weaken into the background. One safe number anchors the timescale of endurance. A red dwarf can shine for about 10 trillion years, like a clock that keeps running long after most other clocks have stopped. The comparison stays simple. The point is longevity, not precision. This is the era of long embers. Another payoff arrives in plain language. Long-lived stars keep local islands warm in a faint way. Yet the global sky continues to empty because no new bright stars replace the ones that end. The colour balance shifts. The average light becomes redder. The dark gaps between sources expand. A scale shift arrives softly. In the core of a small star, nuclear reactions proceed in a compact region. In the space between stars, the void is immense and cold. The energy that leaves the star enters a vast volume. It spreads. It becomes less able to do work. The same process repeats on larger scales. A galaxy becomes a loose collection of long-lived points. A cluster becomes a few galaxies in a broad dark sea. Another visual anchor supports the cadence. A low-mass star sits near a thin disk of gas that is barely present. The disk is faint and patchy. Its outer boundary is ragged. The payoff follows. With little gas left, star formation slows. The system becomes one of aging lights rather than new ones. The disk is a physical trace of earlier abundance. Its thinness is the mark of depletion. The section now focuses on cooling and fading as a kind of gentle arithmetic. A white dwarf begins hot and bright in a narrow range. It cools by radiating heat into space. As it cools, its spectrum shifts. Its brightness declines. The cooling curve is slow at late stages. The object becomes faint in visible light. It can still radiate in longer wavelengths for a very long time. The payoff arrives. Cooling does not remove the object. It changes which part of the sky it belongs to. In visible light, it becomes absent. In infrared, it remains present as a weak ember. A new analogy carries the idea without repeating earlier ones. Consider a stone that has been warmed by sunlight and then placed in a cold room. The stone stays warm for a while. The warmth can be felt close by. Across the room, the effect is minimal. Over time, the stone reaches room temperature. Nothing dramatic happens. The difference fades. The reason it matters is immediate. A stellar remnant is like that stone on a cosmic scale. It is a reservoir of heat that slowly equalizes with its surroundings. Another visual anchor returns to the red dwarf field. Many faint red points appear in a loose distribution. The space between them is wide, their light overlaps only slightly. The physical detail is the gentle fall-off of brightness that leaves deep black between halos. The payoff follows. A sky filled with faint red points still feels empty because the darkness between them dominates the view. The emptiness is not a void of objects, it is a void of illumination. The section now offers a limit of intuition. Intuition expects that something long-lived must remain important. In cosmic terms, even 1 trillion years is a chapter. The largest changes happen on scales that dwarf ordinary imagination. Long-lived stars delay darkness. They do not prevent it. Another limit follows and names a clear observational boundary. The far future light from these faint sources will be hard to separate from background radiation and from dust emission within their own galaxies. Detection becomes model-dependent. The faintest objects are inferred by their gravitational effects more than by their light. The cooling curves themselves depend on interior composition and on envelope properties. Those details are not directly measured for the faintest stages. The broad story remains reliable. Emission fades, visibility shrinks. Another payoff arrives in calm language. As stars age and remnants cool, the available gradients become smaller. Less energy is released per unit time. The cosmos becomes quieter. Processes that rely on strong radiation become rare. The empty volume becomes the main sink for heat. Another visual anchor settles the section toward its close. A white dwarf drifts in a dark region of a galaxy halo. Its light is barely a pin. Its surroundings are empty except for faint background glow. The physical detail is a crisp point on a smooth field with no visible structure around it. The payoff arrives as a final unlock. The universe becomes empty partly because the last lights are conservative. They spend their energy slowly. They keep local islands faintly lit while the larger cosmos continues to stretch and cool. The transition stays soft. The next section resolves the arc by widening to the final quiet state where gradients fade further and the universe settles into a calm, sparse simplicity without any sharp ending. The deepest quiet arrives as a kind of balance rather than an ending. The universe becomes empty because the remaining differences in temperature and density fade into a smoother state. At this distance, light behaves as a slow equalizer that never stops spreading. Only 3 concepts guide this last section. Background radiation is the faint glow left from a hotter early universe. Thermal equilibrium is a state where net heat flow is 0. Entropy is the tendency for energy to spread into more uniform forms. One term receives a short definition and then returns to plain language. Thermal equilibrium is a state where net heat flow is 0. A calm analogy follows. Consider fog that settles into a wide valley. The fog starts as patches. It then fills low places until edges soften. The reason it matters is simple. The far future trends toward that kind of smoothness. A visual anchor opens on a vast dark Morse with a barely present glow. The glow has no direction. It looks the same in every region. There is no sharp boundary. There is only a gentle gradient that is almost flat. The first payoff arrives. Empty does not mean nothing exists. Empty means differences stop drawing shapes in light. Another visual anchor shifts closer. A small group of faint stars remains in a bound island. Their light is weak and red. Their halos barely overlap. The darkness between them is wide and clean. The payoff follows. Local islands can persist while the wider sky loses new texture. The map becomes smaller. The emptiness becomes more complete outside the island. Another visual anchor moves outward again. The background glow becomes the dominant light. It is not a point. It is a thin haze spread across all directions. The physical detail is its smoothness. There are no filaments in it. There are no edges in it. The payoff arrives. When the background dominates individual sources, stop defining the scene. A single number anchors scale without strain. The background radiation is at about 3 Kelvin. It is colder than starlit rock in deep night. It is still not absolute zero. It is a remaining whisper of heat. The payoff follows. Even a small temperature implies photons still exist. The sky is never perfectly dark, it is only more uniform. A scale shift arrives softly. On the scale of a single atom in a cold cloud, motion remains. On the scale of a galaxy group, orbits remain. On the scale of the horizon-shaped sky, expansion keeps widening separations. The same energy spreads into larger volumes. The scene becomes harder to mark. Another visual anchor steadies the cadence. A faint cloud of gas drifts in intergalactic space. Its edge is irregular. Its interior is nearly transparent. A thin gradient of density fades outward. The payoff arrives. Gas can remain present while becoming almost invisible. Scattering becomes too weak to outline it. Its emission shifts into bands that blend with the background. Another visual anchor follows. A white dwarf remnant is now almost indistinguishable from the dark. It is a point that appears only with long patience. Its glow is pale and thin. The payoff arrives. Cooling turns objects into background. The same object remains in place. Its radiation becomes too soft to dominate any scene. The section reaches a gentle limit of intuition. Intuition expects emptiness to look like a void carved out of space. In the long future, emptiness looks like sameness. There is still matter. There is still radiation. The difference is contrast. Another limit follows and names an observational boundary. Such a future state cannot be observed directly. It can only be inferred from present expansion and from physical laws. Even now, the faintest backgrounds are difficult to separate from local emission. Resolution is limited. Foregrounds overlap. Models are required to subtract them. Those models carry uncertainty. The broad direction remains steady. Differences fade. Light stretches. Arrival rates thin. Another visual anchor keeps the rhythm slow. A region of space between galaxy islands appears as pure black. Within it there is still a uniform glow that does not form shapes. The physical detail is the absence of edges. There is no rim. There is no shadow boundary. The glow changes only as a very slow gradient. The payoff arrives. A scene without edges feels empty because edges are how structure is recognized. When expansion and time erase edges, the sky becomes calm and sparse. Another visual anchor shifts to a bound island again. A few dim stars remain. Around them, space is wide and quiet. Their light falls off with distance in smooth layers. The outer layers disappear into the background. The payoff follows. Remaining light becomes a local fog that never reaches far. It keeps the island faintly visible. It does not fill the cosmos with patterns. A final scale shift arrives. In seconds, photons cross small distances and scatter or pass through. In millions of years, stellar remnants cool and fade. In far longer spans, expansion stretches every wavelength and every interval. The same processes repeat without drama. Another payoff arrives as a closing unlock. The universe is empty for a reason that stays gentle. Emptiness is the gradual loss of contrast as energy spreads into smoother forms. The last image settles. A wide sky holds almost nothing but a uniform glow. A few faint points remain in a small island. Everything else is quiet. The arc resolves without sharpness. The script ends in that steady balance. The remaining darkness is calm and unhurried.